A steel rod can be magnetized by using a solenoid. So each diagram shows the most effective way of doing so. Okay, to magnetize a steel rod using the electrical method, we need to use DC supply instead of AC. AC supply is only used for the demagnetization process. Okay, and to magnetize, right, we need to put the steel rod inside the solenoid instead of outside. So the answer should be A. Okay, there is a current in the solenoid. So how does the strength of the magnetic field at point X, Y, and Z compare? Okay, let's look at point Y. Point Y is directly in the center of the solenoid. So we can say that the field strength at Y, it must be the strongest. And for point X and Z, they are at equal distance from the solenoid. So we can say that the field strength should be the same at X and Z. So we look at the option. The answer should be equal at X and Z, but stronger at Y. B. Okay, which diagram shows the direction of the force F that is produced by a current I in a magnetic field? Okay, using the Fleming's left hand rule, we can find out the direction of the force. For option A, the force should be coming out of the paper. And option B, the force should be going in to the paper. And option C, the force should be going to the left. So option D is the answer. Okay, let's just show the Fleming's left hand rule for option D. The current is going upwards, so the middle finger must point upwards, and the field is going from north to south. It should be going downwards, and the thumb, which indicates the direction of the force, is going to the right side. So D is the answer. A bar magnet is pushed steadily into a long solenoid connected to a sensitive meter. So the solenoid here will experience a rate of change of magnetic flux linking the circuit, and it will induce an EMF and current that will cause a deflection in this meter here. So according to Faraday's law, the magnitude of the EMF and current induced is proportional to the rate of change of magnetic flux linking the circuit. So if we look at the option, right, A, how fast the magnet is pushed into the coil. The faster the magnet is being pushed in, the larger the rate of change of magnetic flux linking the circuit, and hence the magnitude will be higher. So A is the correct answer. For B, C, and D, they will just affect the direction of the induced EMF and current, so they will not affect the magnitude of the deflection. Okay, we have a transformer operating a doorbell. So this is the primary coil, and this is the secondary coil. So on the secondary coil, we have a bell that is running at a 12-volt supply. And the bell has a resistance of 8 ohms. And we can find out what is the current in the secondary coil. It will be just V over R. 12 divided by 8, we have 1.5 ampere. So now using the formula, power in the primary coil is equal to the power in the secondary coil. We have Vp Ip is equal to Vs Is. So that will be 240 times Ip is equal to 12 times 1.5. So our current in the primary coil will be 12 times 1.5 divided by 240. We have 0.075 ampere. Answer A.